So now let's see some examples where the limit does not exist. So consider the limit as xy goes to 0, 0 of x squared minus y over x minus y. So let's try to evaluate this. We'll approach 0, 0 along the line y equals mx. And I guess m should not equal 1 in order for this to be well defined. So we need to have x not equal to y. So then we would be looking at lim x goes to 0 of x squared minus mx over x minus mx. So this is x times x minus m over x times 1 minus m. And then we can cancel the x. And now we can just put in 0 for x, now that we've canceled that. And so this limit will be, let's swap the negatives, so m over m minus 1. In particular, this will depend on the slope of the line we chose. It depends on the value m. And so therefore, this limit does not exist. So this demonstrates an important principle. So if f of xy approaches two different limits as we approach x0, y0 along two different paths, then the limit as xy goes to x0, y0 of fxy does not exist. All right, here's a second similar example. Let's look at the limit as xy goes to 1, negative 1 of xy plus 1 over x squared minus y squared. And we'd better have x not equal to plus minus y in order for this to be well defined. So let's try approaching this along two different paths and see what we get. So first we'll try along the line y equals x minus 2. And you can see that that does indeed include this point. So if we do that, then our fraction will become x squared minus 2x plus 1 over x squared minus 4x plus 4. So that's x minus 1 squared over 4x minus 4. So that's 4 times x minus 1. We can cancel an x minus 1 in the top and the bottom. So this becomes x minus 1 over 4. And that goes to 0 as x goes to 1. Right, now let's try along a different line. So let's try along y equals 2x minus 3. And again, we can see that that includes this point. So now our fraction becomes 2x squared minus 3x plus 1 over x squared minus 4x squared minus 12x plus 9. So the bottom is going to be negative 3x squared plus 12x minus 9. So we can factor the top. The top is 2x minus 1 times x minus 1. The bottom, we can factor out a negative 3, and then we'll be left with x squared minus 4x plus 3. And that factors as x minus 1, x minus 3. Then we cancel this from the top and bottom. We get 2x minus 1 over negative 3x minus 3. And now we can just plug in. So as x goes to 1, this goes to 2 minus 1 would be 2 over negative 3 times negative 2, 1 over 6. And so since these two answers do not agree, we get that the original limit does not exist. Here's a final example. It's a bit more subtle. So let's look at the limit as xy goes to 0, 0 of 2xy squared over x squared plus y to the 4. So first, well, let's approach this along the line. It'd be easier for me to just write it as x equals my. So then this will become lim y goes to 0 of 2my cubed over m squared y squared plus y to the 4. So now we can cancel a y squared from the top and bottom. So this becomes lim y goes to 0, 2my over m squared plus y squared, and that goes to 0 as y goes to 0. So we get the same limit no matter which line we use. However, let's try also approaching this along a path which is not a line. So we'll approach along the parabola x equals y squared. So then we'll be looking at lim y goes to 0 of 2y to the 4 over y to the 4 plus y to the 4. And so this is equal to 1. So we get different answers when we use straight lines versus when we use a parabola. So this reveals something that's surprising. So in ordinary calculus, we know we can check for a limit just by checking the left-hand limit and the right-hand limit. But in higher dimensions, having the same limit along all lines approaching x0, y0, this does not guarantee that the limit as y goes to x0, y0 of f xy exists. It needs to have the same limit along all paths which are approaching this point, not just straight lines.